All right, so topic of today's video, extreme values of functions. And I can't say that with whatever problems you see, wherever you see them, whether it's on WebAssign or whatever class you're taking or whenever you're watching this, I can't say that I'm using the exact same vocabulary that everybody else is going to use. But when I say extreme values of functions for right now, I'm just saying that, well, there could be a function, a graph, a curve. You can call these lots of different things if you want to. There might be some point on it that is higher up than all the other points, right? And we would call that an absolute maximum. But, I said that the vocabulary is not uniform. It's not everybody uses the words the same way. So this might also be called global maximum. All right, so I just need to mention that kind of as a disclaimer in case you hear somebody say that sometime. But look at that curve right there. Say I draw this graph, all right, and I say, well, that point right there, that's the number that's the biggest. That's greater than all the other points. It's higher up on the curve than all the other points. You see what I'm trying to say? All right, so we would call that an absolute maximum if there were such a point, okay? So I guess it all depends on the shape of the curve. Look at this other one over here. This curve does not have an absolute maximum. It does have an absolute minimum. It has a point on it that is the absolute lowest point on the curve, right about there, all right? So you know what an absolute maximum is for some function, some curve, some graph. You know what an absolute minimum is, all right? But take this one, okay? So this point, or this curve right here, this graph, this function, it doesn't have an absolute maximum or a minimum. Just by the nature of the shape of this thing, there's no point that's the highest point on the curve, or there's no point that's the lowest point on the curve either. It does have like this point and that point though, all right? So we have other words for that, all right, more vocabulary. That would be called a local maximum. That point right there at the top of this peak, local maximum. And we say local because, well, it's for the whole curve, it's not the highest point, but at least in this region, this neighborhood right here, it is the highest point. It's higher than all the ones on the left, and it's higher than all the ones on the right. So that's what we call it a local maximum. And then this point's a local minimum, meaning that it is not the lowest point on the curve, but it's lower down than the ones on the left and right on either side of it. Okay? All right, so, in not too technical terms, that's the vocabulary that we encounter in what we're going to start doing now. Okay? I would say just generically, like everything I pointed out here is an extreme value of one kind or another. All right? Okay, so let's begin with like a specific kind of problem. All right? So here I wrote out all these notes and everything, but I'll go through several examples. But it says how to locate the absolute maximum and minimum points for a function that's continuous on a closed interval. All right. So that's a very specific kind of problem, and if you read all that and your mind just kind of glosses over, well, I'll show you some examples. But here are the steps. You find this thing called a critical number, which is just a point on the curve, the function, where the derivative is either 0 or undefined. And then you compare the endpoints of the interval to the critical number, and you figure out which one's the biggest and which one's the smallest. So I guess as far as math goes, like it might be that this is a fairly simple procedure, all right? I can think of way worse and more difficult things in math besides this procedure right here. But let me tell you a little bit about why the problem is a closed interval. Why do we have to look at a curve on a closed interval? All right. So real quick, I might say, let's use your imagination a little bit. Suppose this is the curve, okay? So f of x right here. This is a function. If you were to draw its graph, then you get a curve. And as it is, if this is what the function looks like when you draw the graph, there is no absolute minimum because it goes down forever, and there's no absolute maximum because it goes up forever. There is no point on here that's the highest or the lowest point. There just isn't. But what if I look at it on this window? Okay? So in other words, suppose we only see what's in there. We don't see the rest of the curve. We just see that part. All right? That window is what a closed interval is. So when I look at this problem that I'm about to do, I say find the absolute maximum and minimum on that interval of this function or curve. It means I'm looking as this thing spans the x-axis from -1 to 4. So that would be like a defined viewing window. Okay? Now, all right, well, that changes everything. This curve as it is doesn't have an absolute maximum and minimum. But on this viewing window, that point on the far right edge, that's the absolute maximum. And then this point right here, that's the absolute minimum. Okay. All right, so that's why the procedure is that we find the critical number and we compare with the endpoints and we find out which one of those is the biggest and the smallest. Now, a little bit real quick about a critical number. It says here, a critical number is a number where the derivative is 0 or undefined. How about, I don't want to talk about the undefined yet. So let's say a critical number is a point where the derivative is 0. Why is that part of this procedure? Do you see that lowest point right there? What's the slope there all the way at the bottom? Like say the curve dips down like so. What's the slope there at the bottom? The slope would be 0. Because at the very bottom, if you look right down there at the very bottom of it, it's horizontal. Okay, so the reason why the derivative being 0 plays into all this is because it finds those points where the curve might dip down to a low spot or rise up to a high spot. Okay, all right, but that's the thought process, and if you want, you can just not think about it and just go through the procedure. I hope that's not the way you see it, but you know, it's not like it's against the law to just mindlessly go through the procedure. Anyway, all right, so here we go. Let's do this one. Find the absolute extrema on that interval for this function or graph. About this interval, -1 to 4, that's a closed interval. Here's another way to say that. It's like saying I'm going to look at the graph as it spans the x-axis from -1 to 4 inclusive, meaning -1 to 4, including the -1 and the 4, and all the points in between, okay? All right, well, I got my procedure outlined. It says first I'll find the critical numbers. 1. What are the critical numbers? Well, okay, so why did I write that? Critical numbers. I need to find the derivative. So f prime is 2x. And a critical number would be a point where the derivative is either 0 or undefined. Well, 2 times x is never going to be undefined. There's always going to be an answer to 2 times a number. You get your calculator, 2 times a number. There's always going to be an answer. All right. So I will set that equal to 0. That will be how I find my critical number. I'll find the derivative. I'll set it equal to 0. And then if I solve it, I'll divide both sides by 2, and I'll get 0. All right. So my critical numbers are 0. And that's not my ultimate answer, but there's my critical number. Okay. Second part. Compare the function value at the endpoints to the function value at the critical number. All right. So maybe I'll do that by making a table. I mean, you can do it however you want to, but like I'll say, well, here's the table. Here's x, and here's f of x. And almost want to think of this like this is a way for me to see the graph, okay? So x squared minus 9, okay? So I'm going to write the endpoints of my interval, my window. That's -1 to 4. And also the critical number, 0. So see what I got here? This is the left endpoint of my interval. This is the right endpoint of my interval. And this is the critical number. And I should just have to compare those to find out for this curve on that interval what the absolute highest and lowest points are. Okay, so I'll put my numbers in. So -1 going in here, that's going to give me -8, right? 0 will give me -9, and 4, 16 minus 9, that'll give me 7. Okay, and so I can tell, like, just among these numbers right there, that's the absolute smallest of them, -8, -9, -7. And right here, that's the absolute largest of them, okay? So think of it like this. When I make this table, these are actual points on the curve, okay? That's the lowest, that's the highest, because that's the smallest number and that's the biggest. If you would like to, remember I showed you this example before. I said this curve as it is has no absolute maximum and minimum, but on that defined window right there, that's the minimum and that's the maximum. Oh, the critical number in the middle turned out to be the minimum. The right endpoint turned out to be the maximum. So it's kind of like this one. If I see, well, it's at -8 on the left-hand side, it dips down to -9, and then it rises up to 7. It's sort of like, you know, looks something like that. I mean, this is not to scale, but on our window, our viewing window, which was -1 to 4, this is what we're seeing. This point right here is 4 and 7. This point here is 0 and -9. And this point is -1 and -8. Okay, yeah, that's the lowest, that's the highest. Okay, so let's write our answer like this. Probably we will be asked to write our answer in ordered pairs, and ordered pairs a point. A number is not really the minimum or the maximum, but because this is a curve, a point is a minimum or a maximum. So the absolute maximum, well, that would be this one. 4 for x, 7 for y, that point on the curve, or at least the part of the curve we see through our window. And then the absolute minimum is going to be at 0 and -9. Okay, and that will be our final answer to the question. The question being to find the absolute extrema, meaning the absolute maximum and minimum. On the interval, it's those points, because on the interval, we see this part of the curve only, okay? All right, now I know there's more to the curve, right? This is a parabola. There's definitely more to it, but we're only looking at it on that window. We don't see the rest of it, okay? All right, so now I want to just take some different examples, kind of like this one, that might be harder and vary a little bit in difficulty from one to the other. Okay, so let's do this one. So same question, different curve, different graph, different window. Find the absolute extrema of that function on that interval. Well, so it will start with finding the critical numbers. Okay? And those are points where the derivative is either, let's say, 0 or undefined. Okay, so we know how to find the derivative, and we could solve it for 0, or we could figure out where it's undefined also. I haven't talked much about that one yet, but that is part of it, and we'll run into it eventually. So let's start there. F prime. How do you find the derivative of 3x to the 2/3 power minus 2x? I'd carry down the 3. I would get a 2/3, an x, a minus 1/3, and that would be that, and then a minus 2. All right, so we've learned how to do that already. So for f prime, I'm going to get, with the 3's canceling, 2 over x to the 1/3 minus 2. All right. Okay. So first of all, this could be undefined for sure. What does undefined mean? Well, undefined is, say, dividing by 0. That's undefined. Okay. Yeah, dividing by 0, undefined. So could this be undefined? This could be undefined if x was 0. What's 0 to the 1/3 power? What else does this mean? The third root. What's the third root of 0? It'd be 0. So I get this critical number at 0. Okay. Anything else? Well, so critical numbers are the points where the derivative is 0 or undefined. Okay. I did undefine. What about 0? So I'll set equal to 0 and I'll solve it. And I'll get 2 over x to the 1/3 equals 2. And then if I multiply by x to the 1/3 and divide by 2, I'll get x to the 1/3 is 1. And it's like saying the cube root of what is equal to 1, and that would be 1. Okay? So my critical numbers are 0 and 1. Okay? All right. 0 because it makes the derivative undefined, and 1 because it makes the derivative equal to 0. So that's why they are the critical numbers. Only one of these critical numbers is in that window, though, and it's 0. 1's not actually inside the window. It's there on the edge. Okay, so 0 is the only one that we have to contend with. All right. Why is that? Well, because we compared the left endpoint and the right endpoint of the window with the critical number. All right. So I got 2 critical numbers. Only one of them is in play here. So my table is going to look something like this. All right. So x and what's my graph? My curve is going to be this thing. Okay. That's my function. I'm trying to figure something out about the way this looks if it was graphed. All right. So f of x is equal to 3x 2/3 minus 2x. I'm going to start with these numbers. My left endpoint is -1. My right endpoint is 1. The critical number that's between them, that's in play, is only going to be the 0, right? But all we need to do is compare the left endpoint, the right endpoint, and the critical number. All right. So we'll put our numbers in and see what we get. I'll probably pause it to do that to save a little time on the video, but here I'll fill this thing out. All right, so that's what you get. A word about doing like that power. All right. Say you use your calculator. You might, depending on your calculator, you might encounter some problems putting -1 in there. So if I was going to do, like, real quick, let's say I'll do up here. X to the 2/3 power means the third root of x squared. Okay. So when I put -1 in here, in there, that looks like -1. Third root of -1 is -1. -1 squared is 1. Okay. So that looks like 3. And -2 times -1 is 2. 3 plus 2 is 5. All right. So, okay, let me put a note in about it. Do 3, third root, -1 squared minus 2 times -1. And that's how we'll get 5. All right. Looking at that, this point's the highest, this point's the lowest. 5's bigger than 0 and 1. 0 smaller than 5 and 1. Okay. So that's our absolute maximum and minimum. What does this curve, that curve's hard to imagine. What does it look like on that interval? it starts at 5, it dips down to 0, and it rises up to 1. All right? So, I mean, this is not to scale, but it's fairly close to what it looks like. Here, see those numbers on that chart? It tells me that on this window, this curve looks roughly like this. This point is 1 for x, 1 for y. That point is 0 and 0. This point is negative 1 and 5. That's the absolute maximum. That's the absolute minimum. Okay? So let's always state our answer. Apart from our work, absolute maximum is the point, negative 1 for x, 5 for y. And our absolute minimum is 0 for x, 0 for y. Because it looks like this, where that point's the highest and that point's the lowest on that window. All right? Okay. So let's do this one next. And I won't do this one like I've done the others. Okay? Here's why. Think a little bit about, I mean, for this one, I can't blame you if you don't know what that looks like. I end up telling you that I don't know what the entire graph looks like, but on that window right there, this is definitely the window that we're looking through to see that graph. On just that window, this is what it looks like. Okay? All right. Now I can tell that much about it. Think about this one, though. Like, that's not a complicated graph. This is a line that has a negative slope. Okay? So why not think of it that way? Why not? I mean, since we know that about it. So it hits the y-axis at 8, and it has a slope of negative 1. All right, so something like that. Okay? And what's our window? Our window's negative 2 to 1. So we're looking at it like kind of through there, where this is negative 2 on the x-axis, and this is 1 on the x-axis. That's what we mean when we give the interval or the window. Well, so this point would be the highest, that point would be the lowest, right? That's how it'd have to work. I'm not saying this is to scale or anything, but qualitatively that picture is accurate, all right? The left endpoint is the highest, the maximum. The right endpoint is the lowest. There's no critical number. Why not? Well, because there's no point in the middle where it like turns around from having a slope of 0. Okay, so that's why. All right, so no critical number, but we'll say you did the math. You'd find y prime to be negative 1. Okay, what is a critical number? A critical number is a point on the graph where the derivative would be either 0 or undefined. Well, if the derivative is 1, 1's not 0. Okay, and if the derivative is negative 1, negative 1's not undefined either. Okay, all right, so it's got no critical number. Let's just find these points. What's this point right there for x is negative 2? That's going to be 10. So negative 2 for x, 10 for y. 8 minus negative 2 is the point, the y coordinate on the curve. And this point right here, that's going to be 1 for x and 7 for y, right? Because if you put 1 for x, 8 minus 1 is 7. Well, there's your maximum, there's your minimum. There's no critical number in the middle there to compare with, all right? Okay, so let's say absolute maximum. This point right there, coordinates negative 2 for x, 10 for y. Absolute minimum, coordinates there, 1 for x, 7 for y. All right, so let's do one with, I guess like that looks complicated in terms of maybe the derivative being harder to do, like this one right here. 7x squared over x minus 6. Okay? So that's what we have. That does look harder, I would think, than the others. But we know how to find the derivative. You'd use the quotient rule and it shouldn't change it. Okay? So I got my function. I have my window. I can call this the window right here if I want to. Or viewing window if you like that. I can think of it like that I'm looking at the graph as it spans the x-axis from -3 to 2. All right, that's all the ways I can think about it. But however I think about it, we start by finding the derivative as a means to finding the critical numbers. Okay, so let's see. Here I would have to use the quotient rule, like I was saying. So here goes, quotient rule. We've done this lots of times by now. It's going to be 14x, the derivative of 7x squared, times x minus 6 minus 1, the derivative of x minus 6 times 7x squared. Okay, so in other words, like that. And I get 14x minus, 14x squared minus 84x through multiplying minus 7x squared. Okay. And then one more step. So 14x squared minus 7x squared, that's going to be 7x squared minus 84x. Okay. And then x minus 6 squared. So there's my derivative. So I'm gonna put f prime x is equal to that. Now, at this point, I would like to figure out what it takes for this to be 0 or undefined. Okay? So I'll do that over here. So f prime x being undefined. I guess you could say that this is undefined at 6, because that makes the denominator 0. Okay, so 6 is a critical number. It's not in play for us, though, because 6 is not in the window from -3 to 2. All right, so it's a little bit informal for me to write this, but it gets the point across. That critical number is not in play because we are only looking in this window. -6 not in the window. What about f prime x being 0? How do you go about solving that one? Well, that one could happen like this. There's the derivative. I'll take 7x squared minus 84x over x minus 6 squared, and I'll set equal to 0. If I multiply both sides of this by x minus 6 squared, it'll take me to 7x squared minus 84x is 0. All right, 0 times x minus 6 squared is 0. And then I'll factor out the 7. I'll factor out 7x. I think I can do both the 7 and the x. So I'll get like this, x minus 12. Okay. All right, so I'll get two solutions to this. I'll get 0 from that factor right there, because 7 times 0 times -12 is 0. And I'll get 12 from this one. So those are my numbers that cause the derivative to be 0. 12 is not in play either. 12 is not in the interval from -3 to 2. So the only, I guess technically we get 3 critical numbers. 6, 0, 12. But 0 is the only one that is in our window. Okay? All right. So I'll point to that. So that right there, that 0 is the only critical number in the window that I'm looking at. All right? Okay. So our second step, we'll make the table. And we'll compare. All right, so let's see. My table will consist of a comparison between the left endpoint, which is -3, the right endpoint, which is 2, and the critical number within them that's 0. Okay? And that will go in my function. Like so. All right, so I'll complete the table at this point. All right, there's the table. All I did was put my x's in here to get my y. Okay, now, like every time we do this, these are points on the curve. if you were going to draw the graph of that from scratch on graph paper and just connect the dots, these would be some of the points, all right? I use the derivative to find the critical number, but I use the original function. I use its equation to find the points on the curve, and I'm just trying to look at it and compare which one's higher, which one's lower. So across that interval, this curve starts at -7, it goes up to 0, and then it falls back down to -7. So on our window, we're going to see something like this. Okay, the entire graph of that is much more complicated, but the part we see looks like this, something like this. Okay, maybe not this exact shape with that exact curvature to it, but you know, it starts over here, -3, -7. In the middle, it rises up to 0 and 0, and on that edge, it's down back to -7. Okay, that's the graph from -3 to 2. If you look at the graph as it spans the x-axis from -3 to 2, it looks something like this. Okay, all right, so we see this. So what I would have to say about it then would go as follows. The absolute maximum is obviously this one. Okay, it's going to be the biggest number here. So that's going to be 0 for x, 0 for y. And then absolute minimum, I get 2 points. Like those are on the level with each other. They're at the same height, you could say. So I'd have to say -3, -7, and this other one, 2 and -7. All right, I can't say one and not the other. I'd have to get both of them. All right. Okay, now, but let me emphasize a few things about this before I move on. You know, this is just what we see, right? If you could draw this graph on that window, you would see something like this, all right? But outside of that window, there's more to the graph. Who knows what it looks like? You know, we're not looking out the window, so I'm not concerned with it. There's more to it beyond that. But this table shows us what it looks like on that window. Okay, so I emphasize that much about this so far.